Hello class, we're going to continue today talking about activity effects. So from the last class we summarized that if we had a common ion with a equilibrium that was containing magnesium hydroxide, magnesium ion, and hydroxide ion, that common ion would be present as one of our products and would shift the reaction back towards the solids, causing a precipitation. However, when you have a really high concentration of ions in solution, those ions actually get in the way of the aqueous form of the solid to prevent precipitation. So when you have a whole bunch of calcium nitrate in solution, for example, it prevents the magnesium and the hydroxide from reforming and precipitating out. So to measure the ionic strength of the solution, we use this equation, which we determined was equal to about 0.024. Now, whenever we calculate the ionic strength, we are usually going to have to round. Now, this goes to what is present on page 51 of our notes, which is a table of activity coefficients ionic and ionic strength. So to look ahead a little bit, whenever we calculate an ionic strength mu in units molarity, we have to get to one of these values because one of these headings is going to dictate which column we look in for our next number, which is going to be the activity coefficient. So moving on into starting our work for today, we're looking at the ionic strength and affecting a chemical reaction. So to account for the ionic strength, all concentrations are replaced by activities using this equation here, where the activity of component A is equal to the concentration of A times the activity coefficient A. This is the symbol gamma, which is our activity coefficient. The equilibrium constant expression can then be rewritten in terms of activities. So for example, when we have A reacts with B to form C and D, our activity A, this is going to be one of our reactants. But this could be any component. It could be B, the other reactant, or C or D, either of our products. So we rewrite our equilibrium expression. So first we have K equilibrium is going to be equal to the activity of C and D divided by the activity of A and B. And then we can substitute in our concentrations and our activity coefficients to get this expression for our equilibrium, which are the products C and D, their concentrations raised to their coefficients, multiplied by their activity coefficients gamma, also raised to their coefficients, divided by the reactants A and B, their concentrations and their activity coefficients raised to their coefficients. So what does this mean? Well, if we had gamma was equal to 1, that would sort of mean like we had 100% of that component. So in that situation, if gamma were equal to 1, we can use A as an example. If that were equal to 1, then it would just be the concentration, because the concentration times 1 is equal to the concentration. So if all of these gamma values in this K equilibrium expression were replaced with 1, we would just have concentrations raised to their coefficients divided by concentrations raised to their coefficients, which is our very normal version of K equilibrium. However, if our gammas were a different number, for example, a fraction like 0.1, this would have a very large effect on concentration because you'd be multiplying each component by each concentration by a gamma of 0.1. It's really only 10% of that concentration. So it ends up having a very large effect the smaller the value of gamma. So let's write the KSP expression for calcium nitrate with activity coefficients. So KSP is going to be equal to the activity of calcium times the activity of nitrate squared. Because remember, there are 2 equivalents of nitrate for every 1 equivalent of calcium. So this ends up being the concentration of calcium times its activity coefficient times the concentration of nitrate squared times the activity coefficient for nitrate squared. And we're going to get these gamma values on that table that I showed. So what does activity have to do with ionic strength? So our ionic strength that we've calculated is going to affect our gamma, which is going to be a value we get from a table, which then affects our concentration, which has an effect on activity, which has an effect on the equilibrium and solubility. So let's show an example. An effect of a non-common ion on molar solubility. This is a situation where we have no common ions, but we have a really high amount of ions in solution, which is preventing our aqueous forms from precipitating out as a solid. So calculate the molar solubility of magnesium hydroxide in a solution of calcium nitrate. So here we have our concentrations to begin with. First, our magnesium hydroxide is all solid, and we have no product yet. So magnesium and hydroxide both begin as 0. Magnesium increases by x, hydroxide increases by 2x, given the fact that it has a 2 coefficient. We can then use our solubility product, KSP, is equal to 8.99 times 10 to the negative 12th. That's going to be equal to x times the quantity 2x squared, which are our values at equilibrium. This multiplies out to being equal to 4x cubed, and then we solve for x and we get 1.31 times 10 to the negative 4th. When we solve for x, that is our molar solubility. It turns out that the concentration of magnesium is equal to x, which is 1.31 times 10 to the negative 4th, and the concentration of hydroxide is 2 times our molar solubility, which is 2.62 times 10 to the negative 4th. We can now calculate the ionic strength of the solution before we see what effect the calcium nitrate has on this equilibrium. So this is magnesium hydroxide without calcium nitrate. So if we have calcium nitrate and it dissolves completely into solution, that is how you know whether or not a ionic salt is either going to dissolve completely or have a KSP. It's going to really have to be given to you. Some salts, like magnesium hydroxide, only partially dissolve into solution, which is why they have a KSP, but something like calcium nitrate or other common salts like sodium chloride, etc., are very, very soluble and they completely dissolve. This information would have to be given to you. So you'd have calcium nitrate, which is 0.015 molar, and dissolves completely into calcium ion and 2 equivalents of nitrate. There's a 1-to-1 ratio between calcium nitrate and calcium ions. There's a 1-to-2 ratio between calcium nitrate and the 2 nitrate that form. So the molarity is twice that of calcium in solution. So we can use our ionic strength equation, mu equals 1/2 times the sum of concentration of components I times the square of the charge of component I. So we have 1/2 times our component for calcium, which is 0.015 molar times plus 2 squared, given that we have a plus 2 charge, plus 0.030 molarity times the square of -1. So this all comes out to be about 0.045, which we're going to have to round up to 0.05 for one of our ionic strengths of our headings. Now that we have this information, we can calculate the molar solubility of magnesium hydroxide with activity. Because until we calculated the ionic strength, we were not able to figure out which values to get from this table. But now that we have an ionic strength, which is equal to 0.05, we know that we're going to be dealing in the second to last column for our activity coefficients. So we now include gamma and activity for our KSP. So KSP is going to be, for magnesium hydroxide, is going to be equal to the magnesium ion times its activity coefficient times the square of hydroxide times the square of its activity coefficient. The table for activity coefficients, gamma, all of these values, these are found in these 5 columns. The table is all broken up by charges. So these are species that have a plus or minus 1 charge. These are species with a plus or minus 2, plus or minus 3, etc. Hydroxide has a -1 charge, and it's found here. And we then bring it all the way over to the second to last column, which is where our activity or ionic strength of 0.05 lies, and we get an activity coefficient gamma for hydroxide of 0.81. And we use that 0.81 for our gamma value for hydroxide. We then need magnesium. Magnesium is found in the section with a plus or minus 2 charge, which is found here. Go over to our second to last column, we find that magnesium 2+ has a gamma value of 0.52, which we use for our activity coefficient for magnesium. We are solving for x, our molar solubility, which is what the question is asking for. We're trying to find molar solubility. So we bring in the KSP, which is 8.9 times 10 to the negative 12, and that's going to be equal to x times activity coefficient 0.52 times 2x squared for hydroxide times the square of its activity coefficient. We end up with 6.52 times 10 to the negative 12 is going to be equal to x cubed, and we can solve for molar solubility, which is 1.87 times 10 to the negative 4th. So that is the molar solubility of magnesium hydroxide when a bunch of other ions are present. We can compare to the beginning of this problem, where we solved for the molar solubility of magnesium hydroxide without any other ions present. So that ended up being 1.31 times 10 to the negative fourth. It is now greater at 1.87 times 10 to the negative fourth. So this mathematically shows that the solubility of magnesium hydroxide increased with calcium nitrate present. So the equilibrium that we were looking at is magnesium hydroxide dissolving into magnesium ion and hydroxide ions. Having a bunch of ions present prevented the precipitation of magnesium and hydroxide from coming together and forming a solid. So the additional ions prevent precipitation, the reverse direction, which has an effect of increasing the solubility. Let's move on and look at another example. So in a very similar situation, we have chromium hydroxide in a solution of calcium nitrate. And that was a typo. That should be 2 equivalents of nitrate for every calcium. So we're going to calculate the molar solubility of chromium hydroxide, chromium 3 plus and hydroxide with a KSP of 6.7 times 10 to the negative 31, a very small KSP. So this problem will look very similar, and it's good practice. So we have chromium hydroxide solid, dissolves into chromium ion and hydroxide ion. We have 3 equivalents of hydroxide, which is always a -1. That tells us that chromium is in the +3 oxidation state. So we have chromium 3 plus, it begins as 0, as does hydroxide. Chromium goes up by x and is x at equilibrium. Hydroxide has a coefficient of 3, so it increases by 3x to make 3x at equilibrium. We then use our KSP is equal to x times quantity 3x cubed, which is 6.7 times 10 to the negative 31st time equals 27x cubed. We then divide by 27 on both sides and take the product and raise to the power of 1/4 to isolate x, and we get 1.3 times 10 to the negative 8th. We now have our chromium and hydroxide concentrations. Chromium concentration is equal to the molar solubility, and hydroxide is 3 times that amount, 3.9 times 10 to the negative 8th molar. In this problem, we are going to use all of the ions that are present in solution to calculate mu. And this is how you should be calculating this type of problem. So we have the ionic strength. So first, we need to include calcium and nitrate, considering that calcium nitrate dissolves completely. So calcium nitrate dissociates to form calcium ions and 2 equivalents of nitrate. And given in the problem, way up at the top, we have 0.01 molar of calcium nitrate. So that tells us that we have 0.010 molar of calcium and 0.020 molar of nitrate, given that it's a 2-to-1 ratio. For this problem, we're going to use all of the ions to calculate ionic strength, and this is how we should do it going forward. So we're sort of building up to this. So now we have mu is equal to 1/2 times the sum of all of our components, their concentrations and the square of their charges, which are shown here. First, we're going to deal with chromium, which has a concentration at equilibrium of 1.3 times 10 to the negative 8th times its charge, which is 3 squared. So the concentration came from here, the molar solubility, which we calculated. Hydroxide was 3 times the molar solubility. It has a -1 charge. Calcium has a 0.010 molarity and a +2 charge, and nitrate has 0.020 and a -1 charge, both of which we determined here. We can then solve for mu, which is ends up being 1/2 of 0.06, which is 0.03, which we then have to round up to 0.05 to match with one of our headings for ionic strength from the earlier page. Now we calculate the molar solubility of chromium hydroxide with activity. So our KSP is going to be equal to chromium times its activity coefficient times the cube of hydroxide concentration times the cube of its activity coefficient. When we go to the 0.05 column again, we are going to use 0.81 for activity coefficient of hydroxide. That's the same as before, but this time if we go down to the ±3 area, we find that we have for chromium 3 plus an activity coefficient gamma of 0.245 given an ionic strength of 0.05. So we can use 0.245 as our gamma value for chromium. We then solve for x. So our KSP is 6.7 times 10 to the negative 31st. It's going to be equal to x times 0.245 times the quantity 3x cubed times 0.81 cubed. We multiply all of our values out, and we can divide by our non-x values to lead us to 1.91 times 10 to the negative 31st is equal to x raised to the fourth. And we take that value raised to the power of 1 over fourth to get to our molar solubility, which is 2.1 times 10 to the negative eighth. And we can compare that again to our value that we calculated earlier for chromium hydroxide without any other ions present. And again, that we see that the molar solubility has increased as precipitation is prevented.